Today we are joined by Tyler Bell for the Boundary Layer Urban and Land Atmosphere Interaction Seminar. Today he's going to be talking with us about ground-based thermodynamic retrievals and weather uncrewed aircraft systems. Tyler is a PhD candidate here at the University of Oklahoma in his third year. You may or may not know that Tyler is also employed full-time at CIMMS, so he balances both the job of a student and a full-time employee, and he does so quite well. If you don't mind, go ahead and hold your questions till the end of Tyler's talk, and then we can have a discussion at that point. So go ahead and take it away, Tyler.
Okay, thanks for the introduction, Liz. As Liz already mentioned, I'll be talking about some of the work I've been doing recently, trying to incorporate weather sensing uncrewed aerial systems into some of the thermodynamic retrievals that we run here at OU. And so first off, my slide's switching. I'll start with a little quick outline, and admittedly, a lot of this talk might seem scatterbrained. And it's just part of the pandemic, part of where I'm at in my PhD, but some of the things I want to talk about are first introducing TROPoe, which is the Tropospheric Remotely Observed Profiling via Optimal Estimation framework. And this is the thermodynamic retrieval that is alluded to in my title. Then I also want to talk about some of the sensitivity tests that I've done with TROPoe related to VORTEX Southeast, which is where CIMMS comes in. And then also after that, talk about some of the work I've been doing trying to incorporate UAS into this retrieval. So while this seems a little scatterbrained, it all does kind of have a common theme. If you were at my seminar last year, you might recognize this figure. So really my PhD is motivated by the need for better boundary layer observations. And I've done extensive work already intercomparing ground-based remote sensing to weather sensing UAS, also using radio science here. And last year I presented off one of the findings that weather UAS really needed improved kinematic measurements. And so I used remote sensing to help improve those kinematics. So now I'm going to flip it the other way and start using weather sensing UAS to try to help improve our thermodynamic retrievals. And so the three things I really wanted to look at here was first evaluating statistical versus thermodynamic frameworks. There is a difference there, but unfortunately, due to data quality issues, I'm going to have to nix that part. But I will be talking about some of the sensitivities that physical thermodynamic retrievals have to the prior. So I'll talk about exactly what that means here shortly. And also start testing some of the sensitivities of this physical thermodynamic retrieval to various constraints that you impose on it. So moving on, first I want to give a quick primer on how TROPoe actually works. So TROPoe is an optimal estimation framework, and it's a pretty common retrieval technique that combines measurements, prior information, and the uncertainties from both of those to determine an optimal estimation of the atmospheric state. In the case of the thermodynamic retrievals I'll be doing, the atmospheric state is mostly comprised of temperature and humidity measurements. And one of the neat things about this retrieval is you can take indirect observations of the atmosphere, such as radiances or brightness temperatures from various passive remote sensors, and you can invert that into estimates of the temperature and humidity profile. So how does this actually work? Well, there's this big, scary equation up here, but I want to try to break that down a little bit. And this explanation is largely based off of a paper that was published last year, which you can access via this QR code. That's a really approachable paper for understanding what optimal estimation is, and I highly recommend it to anyone. So first, I want to talk about some of the key terms within this equation. So X sub A is your prior data set. So typically, the prior data set we use is derived from sounding archives from National Weather Service offices. Typically, we have 20 to 30 years of data that go into this prior, and we use that to basically have somewhat of a starting point and to determine the autocovariances between different levels of the atmosphere at the location of this retrieval. So this is the change in the observation vector y with the change of the state vector x. And so the state vector is your temperature and humidity, whereas the observation vector can be multiple different things. It can be radiances, brightness temperatures. It can also be temperature and moisture measurements from radiosondes, or in the case that I'll be looking at later, UAS. So this is an iterative process. So we need to start with some sort of first guess, and typically we just use the prior as that first guess. And our first guess takes part in the state space. So this is temperature and humidity, and we use some sort of forward model to turn it into the observation space. So if we have a first guess of temperature and humidity and we need to turn it into downwelling infrared radiance measurements, we need to have some sort of line-by-line radiative transfer model to do that. And that's what this forward model is. So we take it and we convert it to observation space. And then the next step is to use the difference between this forward operator and our actual obs, y, and we weight this difference based on the uncertainty covariance matrix, which is S sub y. And we try to determine, well, how far off are we from the actual observations and what adjustments do we need to make? However, to make these adjustments, we have to somehow get back to atmospheric state space, which can't be done analytically because the models are typically very nonlinear. So we do a local derivative, which is the Jacobian, and we're able to convert back to observation or atmospheric state space. And then you can see we're still kind of far off from the truth. So we just keep iterating until basically the retrieval is considered converged when the change in the state space is smaller than the derived uncertainty. So when you're within your uncertainty bounds, we consider it converged. And so that's a really quick overview. The biggest thing to take away is that we need this prior and the autocovariances from this prior to get started. And this will be important here in a little bit. So again, I highly recommend this paper. Scan this QR code. It's a great paper, and it explains it probably much better than I did just now. So where did TROPoE come from? Well, it was originally AERIoe, and if you've been to any BUL seminars in previous years, you've probably heard of AERIoe. So the same retrieval was ported over to Python in 2019. Josh Gebauer deserves nearly all the credit here. It was about 15,000 lines of code that he transcribed from IDL to Python. And one of the main reasons we did this was to make it more accessible to other users, because IDL, for one, isn't free, whereas Python is, and it's also just these days a more common code base. And as we continue adding profilers to our repertoire, having it in Python will make it easier to script, and as we move towards larger and larger networks of these. So, and the name change was motivated because in the past it was only able to bring in AERI data, but now we can bring in other types of data such as microwave radiometers into it as well. So that's a quick overview of what TROPoE is and why it was converted to Python. So now I want to talk about some of the previous results I've presented here before, but I want to go back over them quickly just to motivate the further discussion. Last year, I published a paper about these intercomparisons between weather UAS, radiosondes, and ground-based remote sensing instruments. And these measurements were from two different flight campaigns. One was the LAPSE-RATE campaign, which took place in Colorado. LAPSE-RATE stands for the Lower Atmospheric Process Studies at Elevation, a remotely piloted aircraft team experiment. And during this experiment, there are a lot of different universities out there with UAS and various other sensors, or a couple of extra LiDAR besides ours. And this all took place in the San Luis Valley, which is a pretty high altitude, dry, and hot environment. I also intercompared data from Flux Capacitor, which was just a local campaign that took place at the Kessler Atmospheric and Ecological Field Station, also in 2018. And the unique thing about these campaigns was that the Copter Sonde, developed here at OU, and the Collaborative Lower Atmospheric Mobile Profiling System, or CLAMPS, was co-located for both of these campaigns, and it provided a really unique data set that hadn't really been collected before. CLAMPS is a mobile facility that contains 3 ground-based remote sensing instruments, one being a scanning Doppler LiDAR, so this is what gives us horizontal winds and vertical velocities. We also have an atmospheric emitted radiance interferometer, or an AERI, and so this instrument measures downwelling radiation in the infrared spectrum from the atmosphere, and these spectra contain information about the temperature and moisture, and we can feed this into TROPoe and derive those temperature and moisture profiles. Similarly, we have a microwave radiometer. So this operates somewhat similar to the AERI, but it measures in the microwave spectrum. So it has sensitive to different parts of the electromagnetic spectrum. And then again, if you're not familiar, this is the Copter Sonde 2.5, which was the weather sensing UAS that was used for these intercomparisons. The unique things about the Copter Sonde are that it was specifically designed for thermodynamic and kinematic profiling. So all the sensors are integrated into this nose cone here. We call it the scoop. And there's a custom autopilot software to always make sure that there's fresh air going into this scoop so that none of the temperature or moisture measurements are affected by the aircraft itself. And for a lot more information on the Copter Sonde, feel free to see or read Segali's et al. 2020. It's a good paper that goes through all the specifics of the design of the Copter Sonde 2.5. So some of the results from this paper, you'll be seeing a lot of these plots during this talk. I call them my comparison plots, as it's just an easy way to see the differences between 2 data sets. So I want to orient you real quick. On the left-hand side are 2D histograms of point-to-point comparisons between 2 data sources. In this case, it's the AERI temperature on the Y, and the Copter Sonde temperature on the X. And then at the top, there's some statistics that describe the data set more completely. So N is the number of points within the comparison, M is the slope of the best fit line, B, y-intercept of the best fit line, the Pearson correlation here, the mean difference between them. And over here on the right is a histogram of the differences. And this also has a couple statistics, which is like the median difference and the standard deviation of the differences. So that think of this as your kind of uncertainty. And so one of the major findings was right here. While this plot does have data from both flux capacitor and lapse-rate, all of this data here in this dry mode were from lapse-rate. And you can see there's actually quite a bit of spread there in your dew points. So a standard deviation of differences of 1.6, which is reasonably large. And this isn't just seen in the Copter Sonde and the AERI versus the Copter Sonde figures. You can also see it when we compare with radiosondes, which are typically thought as the quote-unquote gold standard of atmospheric profiling at the moment. Just to illustrate this point a little further, here's just an individual time from those data sets, an individual profile. The left is wind speed, middle is wind direction, but we want to concentrate mainly on the right plot here. UAS are the dashed lines, radiosondes are the dotted lines, and the AERI retrievals are the individual dots here. And red is temperature, blue is dew point. So we can see the radiosonde and the UAS tend to line up pretty well. There's some bias going on here in both temperature and dew point, but for the most part, they follow the same pattern. However, if we look at the retrievals, there's quite a bit of difference, especially in the low levels, and there's even some difference in the temperature here where it kind of overshoots this inversion. And that was a pretty common feature that I saw within this lapse-rate data set. So that got me thinking, like, well, what in the world would be causing this? Because typically we haven't had much issue with the thermodynamic retrievals. They've been pretty good overall. And one of the main things that came to mind was our prior. So here's the San Luis Valley. Here's the Moffett School where CLAMPS was located. Our prior, so our radiosonde archive was made with the Denver radiosondes. That's almost 200 kilometers away. But we really didn't have much other choice because we also have the Grand Junction office which is also about 200 kilometers away, or we can go to Albuquerque, which is over 300 kilometers away. So who's to say that there's not, or we would expect differences within or between Denver and didn't really want to use Grand Junction because there's all these different types of terrain effects for the mountains, and Albuquerque is again just really far away. So Denver was our best choice, but it got me thinking. Typically, we didn't think that the prior had a whole lot of impact on the retrieval. So, and we thought that because we figured the power of the AERI observations or the microwave radiometer observations overpowered the effect of the prior. But maybe this wasn't the case because this is pretty different. So the two questions I wanted to address was, does the location of the prior data set actually make a difference in TROPoE? And if it does have an impact, how can we improve these lapse rate retrievals? So at this point, I'm going to make a hard right turn and go to the Southeast United States and talk about some of the VORTEX data that I've been looking at over the past year and a half as part of my CIMMS role. For those who aren't familiar with VORTEX, it stands for the Verification of the Origins of Rotation in Tornadoes Experiment, and this is for the Southeast domain. And it's been going on ever since about 2016. And CLAMPS 1 and CLAMPS 2 have both been deployed multiple times down to the Southeast since 2016, specifically in the northern Alabama region. And until last year, all of the retrievals that we've done from CLAMPS during VORTEX Southeast have used the ARM Southern Great Plains site in northern Oklahoma radiosonde archive as its prior. So that's 1,000 kilometers away. So this kind of provided the perfect opportunity to begin testing the sensitivity of the retrieval to the prior constraint that is used. So immediately I went in and basically redid everything. And instead of using the Southern Great Plains prior, I plugged in a prior that we generated from the Birmingham office down in Alabama. So this next figure just shows the differences between the Southern Great Plains prior and the Birmingham prior that were generated. And the solid line is the mean of the radiosonde temperature profile on the left and mixing ratio on the right. And this dashed line is the uncertainty that we apply to the first guess, which is the prior. So you can see there's actually really not that much difference between the Southeast and Southern Great Plains site. However, the uncertainties do have quite a bit of difference here. And that's just based off of the, essentially it's the 1 sigma uncertainty that's derived from the radiosonde archive. We do inflate the uncertainty here in the lowest kilometer. That's why this gets so wide and kind of weird looking. And that's just so the retrieval has room to wiggle in the lowest part of the atmosphere, where the passive remote sensors tend to have the most information in already. So things to conclude from this are the Southern Great Plains prior has more uncertainty. So there's a larger dynamic range of observations that were observed in the radiosonde archive. And then in the moisture, again, not much difference in the mean value, but there's some decent differences between the uncertainties. And again, this looks weird because you see negative mixing ratio, but in the retrieval, there is a physical constraint to it that you don't get negative mixing ratio because that would just be not right. So that's already taken care of. It's just not shown on this figure. Looking at it a little differently, here's just the mean of the SGP prior minus the mean of the BMX. And on average, there's only about 1.5 degrees of difference. And then about 0.6 to 0.5 for the mixing ratio. And it tapers off as you go up in higher in altitude. So rerunning these retrievals, and the only thing different is the prior that we used. This is what happens. So I'm only going to show 1 month from 1 year just to keep under time because there's a lot of data to analyze here. So this is from April 2017, and it's a time height composite of the differences over all the days in April over 24-hour periods of the run or the TROPoe runs done with the Birmingham prior minus the Southern Great Plains prior. And so immediately what we see, well, there's differences. So obviously the prior had some sort of impact. Interestingly, these differences seem to kind of follow the diurnal cycle. So here's around sunrise, and we start seeing this interesting feature in the lowest levels of the atmosphere. And that's kind of curious. And it's also interesting because we kind of see the opposite in overnight periods. But which one is actually causing this? So let's take a 18Z profile from this point and just take a look and see who's doing weird things. Turns out the Southern Great Plains prior is doing weird things. It's doing this weird squiggle in the lowest 100 meters, and which really isn't a physical thing. And then the Birmingham prior looks quite a bit better here. So to keep things simple, the prior data set does actually matter. And there's a pretty good chance that maybe this was affecting the lapse rate data as well. So going back to lapse rate, I want to talk about some of the tests I've been doing integrating UAS in these observations, because obviously the prior is having some sort of impact. So I want to see if we can improve these retrievals using UAS. So basically I ran 4 simple tests. One, I took the AERI only retrievals using the Denver prior. And then I also put UAS into those retrievals. Again, the only change is adding in UAS. And I should note that the UAS during lapse rate, we're only going up to about 900 meters. So that's where the biggest effect will be. One other thing I wanted to test was the effect that UAS can have on microwave radiometer retrievals, because a lot more people around the country own microwave radiometers. So if they can get improved retrievals using UAS, which are relatively cheap themselves, it's a good reason to look into purchasing UAS, investing in that to try to get better retrievals from these microwave radiometers, which are typically thought of as inferior to AERI measurements. One last thing to note before I move on is all of these retrievals were constrained at the surface using surface meteorological data collected with clamps, and the upper levels where we have less information were constrained using the RAP, and that was only greater than 4 kilometers. So from 0 to 4 kilometers, the only observations except the surface met used in the retrieval are either AERI or AERI+UAS, or microwave radiometer plus UAS. So I had to redo all of the retrievals because the lapse rate data originally was done with AERIoe, and I wanted to move it to TROPoe to make sure that we still did see the same patterns. And it turns out we do. Interestingly, though, the temperature measurements are a little bit better. I'm not sure why that is, but we see approximately the same amount of spread in the dew point measurements. Note that these have quite a lot less points than the original ones that I did, and that's because I'm only looking at times where we had UAS flying, because I just wanted to make sure. Those are the only times I really wanted to concentrate on. So these results are less statistically significant, but they are still significant. So main thing to take away from this figure, we're seeing the same patterns with TROPoe that we did with AERIoe. So what happens when we incorporate UAS into the lowest 900 meters from all these measurements? We do see quite a bit of improvement here. So the standard deviation here is about 0.5 degrees C. And up here, before, it was about 1. So we've reduced our uncertainty, if you want to interpret it that way, by about half. One thing to take note of, though, is that this histogram of differences looks pretty weird when we compare the AERI retrievals to the radiosondes. And I'm not sure exactly why that is. I would expect a more Gaussian result like we do see it kind of up here in the temperature comparisons. but I'm not sure why the dew points are doing weird stuff, and it could just be a coding bug with the plotting. Another interesting thing to note is that the temperature retrievals are also improved, though but to a much lesser extent than the dew points. So looking at how the microwave radiometer does with UAS. So here's the microwave radiometer only runs. You can see a little bit more uncertainty in temperature, so about 0.5 degrees C. And then in dew point, it actually looks like it does a little bit better with moisture than the AERI does, which is curious. And it has a standard deviation about 0.8. Standard deviation of the difference is about 0.8. So now let's throw in UAS again. Well, once again, we do see some improvement here. And again, this histogram does look funky, and haven't quite figured out why that is still. We also see, once again, improvements, a little bit of improvement in the temperature. So based on this first look, we do see improvements from microwave radiometer only to microwave radiometer plus UAS, and AERI only to AERI plus UAS, which is promising. But one of the strengths of a physical thermodynamic retrieval like TROPoe is we do get a posterior correlation matrix out of it, which contains a lot of information about the uncertainties. So next I want to kind of go through some other ways we can look at improvement to these retrievals. And we'll start with turning this autocovariance plot to a correlation plot. So this is what comes out after the retrieval has done its thing. So on the left-hand side, we have AERI only, temperature on the top, moisture on the bottom. Right-hand side, we have the posterior correlation matrix with AERI plus UAS. Again, temperature on the top, moisture on the bottom. And this is just from a clear sky period in the morning that was fairly typical of what I saw throughout the data set, because we can only show one of these at a time easily. The perfect posterior correlation matrix would just be a one-to-one line here of perfect correlation. This means that you have perfect information at each level, and that the retrieval hasn't had to rely on any of the autocovariances from the prior to determine its optimal estimation of the atmospheric state. Now, this upper left figure is pretty typical for an area-only posterior correlation matrix. This is typically what we see. And if we look and see how the UAS changed it, there's not a whole lot of difference. We do see some reduction in correlations in this lowest kilometer of the atmosphere. However, they're not that significant. And looking at moisture, we actually see a lot more. So ideally, we want all these off diagonal components to be 0. So we see better results here. But it's really only confined to the area of the atmosphere where the UAS was present, so surface to about 900 meters. However, we do see this anti-correlation bullseye kind of shift up a ways, and that tells us that we are adding a little bit of information above the area where the UAS was operating, which is a promising sign. But overall, there's not a whole lot of change here. Beyond adding in the UAS into the lowest levels. So let's move on to looking at the microwave radiometers. So again, microwave radiometer only on the left, temperature top, moisture bottom, and then microwave radiometer plus UAS on the right. You can see the temperature correlation matrix looks quite a bit different than the AERI. So, and once again, we see actually a lot of improvement where the Copter Sondes were flying here. In the temperature matrices. But above that, there's not a whole lot of change. There's a little bit, but not a whole lot of change, and it's very, very subtle. Looking at the moisture again, we see pretty much the same pattern as we did with the AERI. So this bullseye, anti-correlation bullseye gets shifted up a little bit, so we're adding a little bit of information above the Copter Sondes, but primarily the most information is added where the Copter Sonde was flying. But what I found curious was that if we look again at the AERI+UAS and compare that to the microwave radiometer plus UAS, these moisture figures look pretty darn similar. So what this kind of alludes to is that if you combine microwave radiometers with UAS, you typically can get results similar to using AERI+UAS and better than AERI only, which is, I think, a pretty interesting finding because, again, microwave radiometers are much more common than AERIs around the US and between different institutions. So if moisture is something you really want to measure well and you're contemplating, do I want an AERI? Do I want a microwave radiometer? Well, maybe a microwave radiometer plus UAS is a good option here. One other way we can look at this is taking the square root of the diagonal of the posterior autocovariance matrix. And we can look at, this just gives us the 1 sigma uncertainty of the retrievals. So this is from the same time. On the left are AERI temperatures, or on the left is the uncertainties from the AERI, on the right from the microwave radiometer. Dashed lines have UAS data included in them. And then the top is the temperature, bottom is the water vapor mixing ratio uncertainty. So overall, the pattern is about what I was describing before. So up to about 900 meters, we see pretty low uncertainties, and it increases more after that. And however, you can see that the uncertainty does decrease a lot all the way up to 4 kilometers. We can see that also in the moisture from the AERI. So down up to about 900 meters, the water vapor mixing ratio is, or the uncertainty is comparable to what the Copter Sonde uncertainty is by itself. And then above that, it's a little bit higher, but overall less than using only the AERI. And once again, very similar story to the for the microwave radiometer. Looking at it this way, you can actually see that the microwave radiometer temperature uncertainties do decrease a decent amount, which is something we couldn't really see very well within that correlation matrix that I showed before. But to me, it's a pretty promising result. And then looking again at the water vapor mixing ratios, same story. Microwave radiometer plus UAS is better throughout the depth of the boundary layer and slightly above. And just to drive home again, here's the AERI plus UAS overlaid on top of the microwave radiometer data. So above 900 meters, it's about the same amount of uncertainty, which is pretty promising. So at this point, I probably look like this. And I almost guarantee you I look like this. Crazy guy, just throwing a bunch of plots here. But my main conclusions are the location of the prior does actually have an impact on the physics or the physical-based thermodynamic retrievals. Additionally, weather sensing UAS observations can improve the retrievals from LAPSE-RATE, which is a good thing because they weren't very good to begin with. And hopefully in the future, I can continue exploring this idea and trying to make sure that weather UAS isn't actually over constraining the profile too much. So say we had a UAV that had bad sensors. We don't want it to have so much impact on the retrieval that the AERI can't correct for those errors. So we want to make sure we're not over constraining things. Additionally, want to determine how often UAS should fly for this to be useful in this kind of retrieval. So for these retrievals, I was using, they were 15-minute retrievals, and the UAS were flying every 15 to 30 minutes, depending on the day. So do we need an hourly flight, 2 hourly, 6 hourly, something to continue exploring there. And then I just want to continue to test TROPoe configurations. For example, the microwave radiometer data here didn't have any elevation scans in them. And if you add elevation scans, you can add more information in the lowest part of the atmosphere. So maybe adding those in with UAS gives you an even better retrieval than we're getting already. So I have some references down in the lower left if you didn't scan the QR codes. And with that, I will take any questions you might have.
Great. Thank you, Tyler. So if you have a question for Tyler, go ahead and please use that raise your hand feature that you should see on the bottom of your screen. at which point I'll ask you to unmute yourself and ask your question. In the meantime, Tyler, I was just curious that since you showed that the uncertainty can be really improved with the UAS from microwave radiometers, are the UAS also an option for providing a post-processing bias correction if calibration is not available for microwave radiometers?
Yeah, I think it could be. The only issue is I don't know if currently the weather UAS can go quite high enough to get enough data to do that. Radiosondes are used all the time for doing this bias correction. I think copter sondes could be used for it, but I think we'll need to go a little bit higher than what we are doing now. So,
Christo?
Hey, Tyler, thanks for the great presentation. I have a question and a comment. So you showed very great results with the US constraints onto these retrievals, which is something that's very promising for integrated profiling systems. I was wondering, from a more technical perspective, are you considering multiple priors when you do that? So you're having, for example, a radiosonde prior, but you're then further adding a constraint from the US and additionally from the surface stations. So that's the question. And then I guess the comment for the dew point non-Gaussian distributions is quite possible, although it's not a bounded variable like, say, mixing ratio. What I've observed in the past is that sometimes the saturation constraints that play a role into defining the range of the dew points may actually also skew the distributions, and that would be something interesting to explore further.
yeah, thanks for that comment. I have kind of explored that before, but it's been a while, so I'm a little bit rusty on that. But you're very, very right, that could be an issue. As far as your question goes, we have not explored using multiple different data sets within the prior because basically we don't have enough data to create significant level-to-level covariances. So that's why we use radiosondes, because we can get high enough into the atmosphere to make these level-to-level covariance measurements. And we have a long history of radiosonde observations. So that's pretty much the reason we're sticking with it. If we can get more observations using weather UAS or whatever to determine this prior covariance matrix, that'd be great. But at the moment, we don't have the ability to, I don't think. I think that answers your question.
Any additional